Okay, so over here on the left, or your right, nope, your left, I wrote some results that we're going to use. These are established results. These are things that you will encounter, except maybe these two. These are things that you will encounter in a class on algebraic number theory. I will point out where we're using these things, and we're going to first allow ourselves, we're going to be able to reduce to a case where we actually know exactly which group, in particular this quotient here, is injecting into. So the plan for the day is to sketch out the proof of the Kronecker-Weber theorem in the case that the discriminant of your abelian number field and the degree of your abelian number field is a power of p, where p is an odd prime. And then as an exercise, I'm going to have you all sketch out the proof for p equals 2, and in doing so, you will also correct an error that I made. It was one that I warned you not to do yesterday. I said something about certain extensions always being cyclic. That was true if you were dealing with p and odd prime. So I forgot the case that you should never forget, which is p is even. Okay. All right, so there aren't going to be many details. I'm just going to try to give you a clear sketch of the proof so that you can see where some of these objects are appearing and why we're interested in them and what they buy for us. All right, so the degree of L over Q is p to the m, and the discriminant is p to the s. Where p is an odd prime. So our goal is to show that with these conditions, L is contained in a cyclotomic extension. The first step in doing this is you show that your prime p is totally ramified in L. And what totally ramified means is you have a single prime lying above p, and there's no residue extension on the finite field side. All of the degree of the extension is accounted for in the exponent. So remember that p is ramified if this exponent here is greater than 1. We say that it's totally ramified if this exponent is exactly the degree of your extension. Okay, so that means that there was nothing happening here other than p becoming what looks like an degree to the degree of L over Q power. All right, how do you do this? Well, since our Galois group is abelian, all of its subgroups, and in particular the decomposition group and inertia group, are normal. One thing this buys us is I can conjugate the decomposition group by whatever I want, but I will not change that group. I'm always just getting back exactly this decomposition group. And exercise, if I had another prime, let's call it p tilde, that appeared in the factorization, then in order to get the decomposition group of that p tilde, I would end up conjugating d of p. Okay? But if conjugation changes nothing, what that means is no matter what other primes might have appeared in the decomposition group here, or in the factorization here, if I run through all of the different Galois conjugates, so do sigma of this, sigma of any other primes that are appearing here, I haven't changed the decomposition group at all. Okay, so what this means is if I do conjugation, which in general would get me the decomposition group of some other prime dividing P. In this case, because the decomposition group is normal, I didn't get anything new. Same thing is true for I. Then let's revisit the diagram that we ended with yesterday. So we have this field diagram. So down here, Q is the only thing fixed by the entire Galois group. Up here, L is fixed only by the identity. Here, this is the subfield of L that is fixed by the inertia group. And this is the subfield of L fixed by the decomposition group. One thing that we get is that all of the ramification for P has to happen in this extension. Okay? Because remember yesterday we said that if D is normal, then all of the splitting happens here, all of the residue extension happens here, and all of the ramification happens here. I have no residue extension, I have no splitting because, actually, yeah, I have no splitting. And so the only thing that happens is I have all of the ramification happening up here. For degree reasons, right? Here, G is 1, F is 1, E is everything, which means that all of the ramification happens here. Sorry, I'm saying things unclearly. All of the ramification happens in this extension. This implies that Li over Q must be unramified at P. Clear as mud? All right. So all of the ramification has to happen, because all of the ramification is happening over here, this means that this extension, so Li over Q, is unramified at P, but that implies that P does not divide the discriminant of Li over Q. And for any other prime, Q will divide the discriminant of Li if and only if Q is ramified in Li. But that would mean that Q is also ramified in L, which means that Q has to be P, but we just said that P is unramified in Li. So Q would be ramified in L, which implies that it divides the discriminant of L. That means that no such Q exists. So this is telling us that the only prime that could possibly ramify in Li over Q would be P itself, but we've just argued that P doesn't ramify in Li over Q. That means that you don't have any primes that ramify in Li. What have I just told you the field Li is? Basically, what this is saying is the discriminant of Li is not divisible by any prime, hence it is 1 or negative 1. What is Li? Ooh. I've mentioned a few times yesterday that there's exactly one number field, one finite degree extension of Q that is unramified for all primes, i.e. only one that has discriminant 1. Someone said it? Q. It's Q. Li is Q. Then since the decomposition group let me not use prime, for any p tilde such that p tilde intersected with z is pz, the decomposition group of that thing is just equal to the decomposition group for the first prime p that we wrote down over there for every such prime lying over p. We have that the decomposition group, or the decomposition field, which is contained in this inertial field, has to also just be Q. That means that there is no splitting. Okay, so far so good? Okay, so what we've just argued is the inertia field is Q, but that forces the decomposition group over P, for P over, so curly P over P, to also be Q, but we argued before that the decomposition group is the same no matter which of the possible Galois conjugates of this P I'm looking at, which means that the decomposition group is always satisfying this, but this is the field, so LD is the field in which all of my splitting is supposed to happen. If LD is Q, that means I had no splitting. Okay. In addition, since the degree of the field fixed by the first ramification group that we introduced at the end of yesterday's lecture is equal to the index of VI in I, which, because we're dealing with finite groups, is just the order of I divided by the order of V. And because of this result over here, we know that the degree of this extension has to divide OL mod P cross. But what we're saying is I have only one prime. I have no splitting. I also have no residue field extension. This really is just isomorphic to FP. So, oops. So the degree of this extension has to divide the degree, or the order of this group. But in the situation that we're dealing with, we basically just argued that this extension, this finite field here, is the trivial extension. So this is just FP, which means that I have to divide P minus 1. But this is a subgroup, so these are, the degree of this extension has to also divide the degree of this overall extension. So I'm asking you to find me an integer that divides something that is relatively prime to P and something that is a Pth power. What is it? 1. It's 1. If the index of this field here, of this field extension here is 1, and this happens to be Q, then what field is L fixed by VI? It's also Q. Sorry, I said LVI and it's LV1 in particular. So this is Q. So far, so good? Okay, and hopefully you're seeing why looking at these higher ramification groups helped us, right? It allowed us to just lean back on divisibility and say, I'm asking for something to divide two numbers that I know are relatively prime. Therefore, that number is 1. Therefore, the degree of the extension that I'm dealing with is 1. Therefore, that field is just Q. And so we'll keep moving along. All right. Next, this I cannot justify, I cannot even define the thing that this involves. It's beyond the scope of what we can cover. I'm just going to tell you that there's a particular integer, and the only thing that we need in order to know what that integer is the degree of a subextension in L over Q. Not delta, this should be an S. And what I know about this integer, if you really want to know what it involves something called a different, and this is the exponent of the different of a particular prime. The different is an ideal. We don't have time to go into what the different is, but it's important. So this integer here, it is going to be equal to, that's definitely not true. It's going to be equal to 2 times p minus 1 for any subextension k. That has degree p. Okay, so this means that if I give you any subextension in here, if I tell you that the degree of that subextension is p, I'm telling you that this integer here, sk, is 2 times p minus 1. I don't need to know anything else about the field extension beyond its degree. All right. Next, we're going to choose j to be the smallest integer such that the jth ramification group is not the entire Galois group. And the exercise that I had you all do yesterday involving, or one of the exercises that involved the high ramification groups, was to show that eventually the sequence of descending subgroups that you have from the higher ramification groups has to end. Eventually it's trivial. That means that there is such a j. Okay. But because we have established that the fixed field of V1 is Q, that means that the index that we use here, this j, has to be strictly greater than 1. Right? So part of what we're getting from this argument before is that the first higher ramification group is the entire Galois group. I know that eventually one of the other high ramification groups is trivial. That means that at least one of them is not the entire Galois group. And so pick the smallest j for which this is true. All right. I claim that the degree of this extension is p. Why is this true? Well, if I want to know the degree of this extension, it helps if I can just say something about some of these subgroups of the Galois group that we're encountering. So I'm just going to choose the right one that allows me to argue that the extension is degree p. Okay. So by our assumption, j is the smallest integer for which the jth high ramification group is not all of the Galois group. This means that this one actually is the entire Galois group. implies that let me tell you what's happening here. So this one must be the entire Galois group because this is the first high ramification group. It is not the entire Galois group. This, according to, which bullet point is it? According to this one, this group injects into OL mod P, but as we said before, OL mod P is FP. So what does this do for us? That means that the result, let me finish saying what I'm saying. Okay, so the degree of this extension has to be the index of, normally I would just have to write Vj minus 1 over Vj, but here Vj minus 1 is the Galois group, so really what I want to know is the index of Vj inside of the Galois group. That is the order of Fp. That is P. Okay. This means the result from 2 holds. And now what we need to show is that this extension is the only extension that has degree equal to P. Okay, so our claim is there is a unique subextension in L over Q of degree P. And this is where that different thing is going to come in. Again, this is a bit of a black box, so this is like a trust me bro moment, but y'all are gonna have to trust me. Okay. What you can do is you can show that if there is another field in the extension of degree P, then this mysterious integer that I can't tell you much about, which because we've already argued that this has degree P, we know that this integer is 2 times P minus 1. You can show that this is greater than SK, but the point of 2 is that SK doesn't depend on the field, it depends on the degree of the extension of the field, and I've just given you another extension of degree P. Would be helpful if I could finish that statement. And this is a contradiction, because I'm saying that 2 times P minus 1 is greater than 2 times P minus 1. That's nonsense. Okay. And now one of the other exercises that I asked you to show kicks in. Since I have a unique extension of degree P, that means on the group theory side, I have a unique subgroup of index P. This is an abelian group. Its order is P to the M. It has a unique subgroup of index P. One of the exercises that I asked you to prove yesterday is that that group has to be cyclic. Okay. Yes? It comes out in the proof, but because we haven't worked with what the different is, and in particular you don't know a way to compute the different based on higher ramification groups, this one this is the trust me bro moment. Okay. Yeah. No, you're not missing anything obvious. This part of the argument here is a complete black box to you. Although I hope that someday you will be inspired to go back and look in Marcus or in Rippenbaum and like open up that black box and see what's inside. Okay. Okay, finally, to finish. We're going to take R to be the P to the M plus 1 cyclotomic field. Then one of your exercises for today is to complete an argument that we started all the way back in lecture 1. So in lecture 1, I asked you to show that the nth cyclotomic field's Galois group injects into Z mod NZ cross. We need something stronger. We want that it's isomorphic to Z mod NZ cross. And so one of your exercises today is to complete that argument by showing that the natural map that we had was a surjection. Okay, but we're just going to use this. So the Galois group of R over Q is isomorphic to the unit group. This is cyclic of order phi of P to the M plus 1. But hopefully you all have seen and remember how you figure out the Euler free function when you're dealing with the power of a prime. This is P to the M times P minus 1. It therefore has a unique subfield of degree P to the M. And we'll call that R prime. Yes?
Should that say there is a unique field of like degree P over Q, or?
Which one?
The first sentence there.
Yes. Yes. Thank you. Good catch. Unique subfield of degree P, meaning unique subgroup of index P. Thank you. Okay. Since P is the only prime that ramifies in R, it's also the only prime that ramifies in R prime. And now we're going to consider the compositum of L and R prime. So we have a field diagram that includes a diagram that looks like this. Here I want to be careful. I don't know that the intersection of L and R prime is Q, so I cannot assume it. I just know that the intersection is some subfield. And over here somewhere, you have Q zeta M to the P, Q zeta P to the M plus 1. Okay, since P is the only prime that ramifies in L, and it's also the only prime that ramifies in R prime, it's the only prime that ramifies in the compositum. This is one of the results that I told you that we would refer to, but we haven't proved. Okay? If I had another prime Q that ramified in the compositum, this would contradict a whole bunch of stuff. Let's not worry about it. What we care about is the fact that L that the compositum LR prime has only one ramified prime, and that is P. But that means that LR prime is another field extension of degree a power of P and discriminant a power of P. And so all of the work that we did before applies again. So conclusion at this point, not conclusion of the proof, but LR prime over Q has a cyclic Galois group. Okay. But if this group is cyclic, every subgroup of this group is cyclic. So in particular, the Galois group of, let's see, the compositum over the intersection is also cyclic. But, and here's the finishing step. It's going to be so good, y'all. Okay. The Galois group, I think I had you all prove this on the first day too. R prime, sorry. This Galois group, it arose as a compositum not just of L and R prime over Q, it's also a compositum of L and R prime over the intersection. That means that its Galois group, because everything we're dealing with is abelian here, its Galois group is isomorphic to the Galois group of L over the intersection times the Galois group of R prime over the intersection But y'all, this is a cyclic subgroup of order p to some power, and it is also a product of two other groups that are also powers of p in order. There's only one way that can happen. So if I give you something, its order is p to some k. This is a p to some, I'm running out of letters, a. This is of order p to some b. And I'm telling you, I took these two p groups. I took a product, and I got something cyclic. Something has to be true. Does anyone remember their group theory? Yeah. One of them has to be trivial. They cannot both be non-trivial groups of order a power of p. If this one is trivial, this means that L over the intersection is not an extension at all. It's a trivial extension. But then that means that L had to have been contained in this intersection, but that means that L was contained in R prime. Or apply the same argument here, R prime is contained in L. But I chose R prime for a reason. It's because the degree of R prime was exactly the degree of L. I've just given you two extensions. one of them is contained in the other and they have the same degree, everything is Galois, this is beautiful. What do I conclude? Don't overthink it, trust your heart. Like look deep into your mathematical heart and say heart. I have one thing contained in another thing, but those things have the same degree. They're equal, they are the same field. We did it. Because what was R prime? R prime was not just a random extension of degree p to the m. Which field did I explicitly choose R prime to be in? Look, all the way back over there. I chose it to be inside of a cyclotomic extension. And I've just explained to you why L is the same as R prime. That means that L is in a cyclotomic extension. Which one? This one. Huzzah, we win, we did it. That's great. We did it. Almost. Future you is gonna actually finish it by doing the p = 2 case, but like, you know, future you, when future you does it, say huzzah. Okay. Got about 10 minutes. So I've outlined how you do this for two. For two, the slight complication and the thing that I ignored two about earlier that I really should have paid attention to is the issue comes down to the fact that I cannot just put a 2 here and get something that is cyclic, not for every power of 2. For example, Q adjoins A to 8, it's not a cyclic extension. Its Galois group is isomorphic to the Klein 4 group. Okay, so you have to do something a little bit different, but even in the case of 2, there's a particular extension that you can pick out that is always going to be cyclic. And that's the bulk of what I'm asking you to do in the exercises today. And then once you find that extension, you just adjoin an appropriate root of unity that is also based on a power of 2, and you still get to the same conclusion. Okay. I know that I still owe you a lemma. There was a lemma that we used in the reduction argument, but because we're running a bit short on time, what I'll do is I will type up the notes that explain how you prove that reduction lemma. So there was the one about if you have a prime Q that divides the degree of your abelian extension but doesn't divide the discriminant, then you can find some other field whose degree divides in the degree of your original extension where you've removed one of those Q factors. That argument also uses high ramification groups, but it's not a difficult argument to sketch through. And so I will type that up and post it in the Zulip, or have them posted in the GitHub. But for the last 10 minutes, I just want to talk a little bit about where you go from Kronecker-Weber. Right, so what Kronecker-Weber gives us, one way to phrase what we've been focusing on arguing for this entire lecture series, is that I can identify the Galois group of an abelian extension over Q with the quotient of the unit group of Z mod NZ for some n. Okay, so it's telling us I can always find some integer n that has a surjection here. Right? you can ask yourself, and you all started doing this yesterday, I was writing a bunch of things about certain decomposition groups and inertia groups in terms of just a field extension over Q, and a few times people said, well, does it have to be over Q? Can you do this over another number field? Like if I give you an extension L over K rather than just L over Q, can you still say the same things? And for everything we wrote yesterday, the answer was yes. And now that you're thinking along those lines, it's natural to ask yourself, can I do something similar if I replace Q with K? And the answer is, ooh, yikes. The answer is, when you make appropriate accommodations for the fact that maybe you're not working with something with a ring of integers that has unique factorization, you have to phrase things slightly differently in terms of the ideals that you're dealing with, you can still recover a similar statement. And so let me tell you what it is. So you can seek to generalize. So you can try this. For an abelian extension L over K, and what you get is a surjection that I'm going to explain in what looks like an annoyingly vague way, but it's because we don't have enough time to define all of the things that would appear on this side. So I'm just going to say, from a certain collection of fractional ideals of K that you know based on the ramification in L, because that's really what our last few steps were about, right? We were restricting ourselves to a case where we really understood the ramification of L over Q. We do something similar here. So you choose a collection of fractional ideals based on the ramification of your extension L over K. And for the right choice, you get a surjection onto the Galois group. And efforts to give some sort of explanation, either some sort of surjection or some sort of explicit description of the polynomials that you can use, or some sort of description, some explicit description of the right functions to consider to somehow explain all of the abelian extensions of your field. That is the goal, or those are some of the goals of class field theory, right? So class field theory over Q is the Kronecker-Weber theorem. And we have something that feels a bit more abstract, and it's something kind of implicit, and that is a class field theory for arbitrary abelian extensions of number fields. And yesterday, Iran talked a bit about one of the other cases for which we have explicit class field theory, which is an imaginary quadratic field. And the headline there is, there are special functions. So you have the J invariant function, and you have an additional function called some Weber function, and you look at special values of that function, and that gives you the abelian extensions of your imaginary quadratic field under the right conditions. That might feel like a real weird pivot, but you should think of the J function and the Weber function as coming together to play the same role as the function e to the z does in the Kronecker-Weber proof. Because we didn't talk very much about the fact that we were picking out special functions of the complex function e to the z, but that is what we were doing when we were picking out primitive nth-roots of unity. Okay? So you can ask for something similar over other fields. Imaginary quadratic fields, we can do that using modular curves. In general, there are some conjectures on how you do that for arbitrary number fields, but except in rare cases. We know that there is some class field theory. What the right objects are to give you the class field theory that you want, something very explicit for a given number field K, that's still an active area of research. And so if this was exciting to you, I hope that you'll keep digging down and learning some algebraic number theory, and then maybe someday you will contribute something new to class field theory. And if you do, make sure you shout out CT&T 2026. Okay, and I will stop there. Thank you.